This lecture, I want to talk about when chirality emerges in molecules that don't have chiral carbon atoms. And so it's kind of the opposite of meso, where we had the chiral carbon atom, but we didn't have chirality. Now remember, chirality is just not being superimposable on a mirror image of, the molecule is not superimposable on its mirror image. And so it, in all likelihood, has an enantiomer. So let's look at examples of this. Now, it turns out that a very common instance is with allenes. And so if we take a second to just, first of all, define what an allene is, it is when we have a molecule with carbon-carbon double bonds on sort of connected. So they're not in conjugation, not alternating double bond, single bond, double bond, but it's when we have carbon-carbon double bonds just attached to each other. Okay, this makes for a very unusual system. Now, what we have to first recognize is that the carbon atom in the center is sp hybridized. And then what that tells us is that we should consider, if it's sp hybridized, we have two vacant p orbitals on that central carbon atom to make room for two pi bonds. Now, two pi bonds shouldn't be a surprise because we've got two double bonds present in the molecule, but let's consider how unusual the pi orbitals are of this allene. So the pi orbitals of an allene are such that what you have is, and this is me drawing pi orbitals, so this is probably going to get messy. Let's start by considering the first pi bond. So I'm going to have carbon, single bonded to carbon. Now, pi bond is when we have empty p orbitals that are, excuse me, not empty, unhybridized p orbitals that are parallel to each other across atoms. And they'll start to actually fold over on each other and overlap. But to show that overlap, I will just have kind of these three lines that will prevent me from getting too complicated in my drawing. Now what we're going to do is have another pi bond extending to the carbon atom next door. Now for this to work, we actually have to twist the vacant, excuse me, unhybridized p orbital so that it's perpendicular or orthogonal to the first pi bond we had drawn, the p orbitals within the first pi bond. So they're going to operate on the z or z axis, Cartesian axis, whereas the first one was on the y axis. So the second pi bond has orbitals that are coming out at us. The first one has them parallel to the piece of paper. Okay, so what that means is that we have two pi bonds that are parallel to each other. Now we have sp2 carbon here and an sp2 carbon here. And these are the carbons that I want to pay attention to. Now for this to work, I'm going to go ahead and just write this. Maybe let's just see what this looks like. Okay. The blue, this doesn't look too bad. Blue is going to be the single bonds at the sp2 carbon atoms. For the adjacent or for the other attached substituents. The two hydrogens are going to be pointing up and down in the y-axis, okay? So they're not actually coming out at the piece of paper, and that just allows us to be sp2 at that rightmost carbon. If you recall, in an sp2 atom, the unhybridized p orbital that forms the pi bond is perpendicular to the other sigma bonds around that sp2 carbon atom. So those two hydrogens are pointing up and to the right, down and to the right, and they're in the plane of the piece of paper. Interestingly, for this to work, the hydrogens on the left side, for them to be perpendicular, they have to have a z coordinate component. That is, one is coming out at us and one is going away. So this is how we get this to work. The two hydrogen pairs are perpendicular because the two pi bonds are the orbitals that make up the pi bonds are perpendicular to each other. So what we have here is sp2 carbons. These things can never have four different things attached to them, but we have a wedge dash and two straight lines. It's almost like the sp3 hybridized atom has been split across the molecule, the center atom being the bridge between the two substituents of a normal sp3 carbon atom. Now what that means is that for our allene molecule, if we introduce different groups on the left and right side, we have the opportunity to form chirality. So what I'm going to do is consider the 4 positions. I'm going to rotate this so the wedge and the dash are on the left or on the right side and the straight lines are on the left side. Okay. So what we have here is, again, think of this as a tetrahedron that's been split across the molecule, our wedge dash pair and our 2 straight lines. Let's put different groups attached to each of these 4 positions. That is, if I have an H here, I have a CH3 here. Let's pick on a Cl over here and an ET over here. Now I drew this molecule quite big, so forgive me, but I'm going to consider a, yeah, the mirror plane would work. The mirror plane. So this is going to be a mirror. I usually don't do it this way, but let's go ahead and give it a shot. If I draw the mirror plane this way, then the ethyl, chlorine look like this. Now the CH3 is going up and the H is going down. That's just what the reflection of this molecule would look like in a mirror plane. Now, if you look at this, we actually cannot superimpose this molecule. I'm just going to drag this up really quick so you can see. Whoop, it didn't work. Okay. Well, hopefully you can see that I cannot superimpose this. If I try to put all of the alene carbons on top of each other so that all of the other atoms are potentially overlapping, the CH3 does not overlap with the H in the original structure. These molecules are not superimposable on each other, and these molecules are actually mirror images of each other. So allenes can be substituted so they are not superimposable on their mirror image. And what that means is they are chiral. And again, my approach to thinking about this is what I could do is just, let me grab that. I'm really not doing well with my selecting today. Okay, is if you kind of merge this over here, that looks like a tetrahedron. We have a wedge dash and then 2 straight lines, and there's 4 different things attached. The same thing, it's sort of, I mean, it works when thinking about the chirality of an allene, but fundamentally it's just, is it superimposable on its mirror image? Okay, now another fairly unusual, well, it's becoming more common, so I shouldn't say unusual, but sort of just another example of seeing chirality. Let me not get too far ahead of seeing chirality for systems that do not have carbons with 4 different things attached would be chiral by, and that's usually not hyphenated, I'm just emphasizing it for you, chiral Biairing systems. And this is called axial chirality. Now here what happens is that chirality emerges when free rotation is not possible. It turns out that a lot of conformational isomers could actually be chiral for just trivial molecules, like very trivial molecules. Like if you have, let me think of an example. If you have like cyclohexyl methyl ether, well, yeah, you can find ways to just draw, you can easily find ways to draw conformational isomers of that molecule so that the conformations themselves are chiral on an otherwise achiral molecule. But it's the opportunity to undergo free rotation to get you to a state which has a plane of symmetry, allowing you to kind of see why this molecule won't rotate plane polarized light. It kind of self-racemizes amongst its possible conformational states. Now, if we make that barrier to free rotation so large that we just can't undergo free rotation, we could have the opportunity to generate real chirality. I mean, it's all real chirality. We could have the opportunity to generate some more permanent chirality. Now, an example is when you have a Biairing system. Now, a Biairing, arine is another word for an aromatic molecule. So like a bibenzene, for example. It's a benzene connected with a sigma bond. And so this is a Biairing. And what I'm going to do is substitute the ortho positions. If I substitute the ortho positions, for example, what happens is when this molecule wants to try to do free rotation, the free rotation is blocked because the groups will start to bump into each other. So this is sufficiently crowded to prevent, I'm going to do free rotation here. Now, what bond am I talking about? This bond cannot do free rotation because we would get to a point where the two rings are parallel to each other, and that would cause the OH and the CH3 groups to bump into each other. And you'd see a more pronounced effect with larger groups, or more guaranteed effect, I guess to say, with larger groups. So there's no free rotation over this central one. And what that means is that the molecule is sort of locked into place. Now, how is it going to lock? Well, if we have the two arenes, if they're connected by my thumbs, they could be pointed this way or this way, parallel to each other, or still parallel to each other, but with the groups facing on opposite sides. If they cannot do this spin, what they're going to do is lock so that they're perpendicular to each other. One ring is going to be flat. The other ring is going to be having an pointing out component and pointing back component. So they'll be rotated to a certain degree so that they start to accommodate that sort of geometry. What you get then is, in this particular case, part that's pointed, part that's flat, and let's have the bottom part be flat, sure. And then part that's pointed towards and pointed away. And maybe I should be, here's what I'm going to do. I'm going to draw the right side of this ring pointed away. And so what that means is that we have a bunch of dashes. Now it's hard to see with these lines. So, but they're dashes, so they're pointing away. Now let's draw some thick, well, I've got this marker here. It's thicker black line because the methyl group is pointing towards us while the OH is pointing away. So it's just sort of locked in that position. Now, if you consider this versus the enantiomer, you would see that it's not, or the mirror image, you would see it's not super imposable on the mirror image. So the axis of rotation, of free rotation, is blocked due to sterics, creating an opportunity for an enantiomeric conformer that cannot sort of get to the opposite enantiomer by free rotation, and so it can't really sort of self-racemize on the time scale that we can observe the chirality, the racemic effects, and we see sort of an emergent chirality on something that doesn't have an opportunity for a more typical permanent source of a more permanent stereocenter. Okay, let's do some more examples. It turns out that, I'll leave this up here, that lone pairs, this is kind of fun, lone pairs can count as a fourth different group when on certain atoms. Okay, so a really good example of this is a sulfoxide. So a sulfoxide would be, for example, dimethyl sulfoxide, DMSO. Okay, DMSO, if you recall, we draw it in this resonance form, and we put the lone pair of electrons on the sulfur atom to remind us that the sulfur has an octet, even though it's positively charged. So this is a good resonance structure, the best resonance structure, I would say. If you wanted to draw it where the sulfur has exceeded the octet, it does not change what I'm saying here, because resonance structures don't change the inherent properties of a molecule, just how we can depict and visualize them. Now, what I want to do is replace one of the methyl groups of the dimethyl core with a phenyl group, for example. If I do that, if you notice now, I have one. I'm going to change the color here. 1, 2, 3, 4 different groups. Now I'm counting the lone pair as a fourth different group. Now what this means is that this molecule is chiral at sulfur. Chiral at sulfur. In fact, if you wanted to try to assign its absolute configuration, that is an appropriate label, what you could do is actually draw the lone pair with a wedge, and for this particular enantiomer, the oxygen then with a dash. And if you try to draw a mirror plane, or you draw the same depiction of the molecule, but you flip the wedge and the dash around, you get back to these things that we have talked about time and time again related to enantiomeric structures. That is, they're not superimposable on the mirror image. Okay. This is quite the thing. This is quite prominent when we have atoms that are in at least row 3, if not greater. Lone pairs on row 3 elements and beyond will do this. So lone pairs on row 3 elements will exhibit this effect. That means we could switch the element around again. And so we could have chiral phosphorus elements. Okay, so chiral phosphorus, for example, if we had ethyl, phenyl, OCH3, then a lone pair of electrons, we would say that this is also chiral at phosphorus now, because that lone pair allows us to have a depiction where, for example, we've got OCH3, a phenyl, an ethyl, and then going back, we could have the lone pair pointing back. It's just one of these groups. There's 4 different groups now if you count that, and you've got a chiral phosphorus atom. Now what's important is this is chiral phosphorus oxidation state 3. Okay, if you look, it looks like it has kind of 3 -1 charge things attached to it. We'll go through some oxidation state approaches much later in the semester, but you could also have other versions of phosphorus that are chiral. So phosphorus actually makes a fairly strong pi bond with oxygen, even when it has 3 other things attached to it. Now, if you look, if A, B, and C are different, phosphorus is now chiral. And you much more often will see this. So this is an example of chiral phosphorus 5. Okay, so phosphorus in the 5th oxidation state will be chiral. And so a common example of this is to couple this effect with some opportunities for axial chirality. That is, if we draw this biaryl system, and it's a binaphthyl system, I have 2 oxygens ortho, and I lock those 2 oxygens together as a phosphorus in the 5 oxidation state. And I've got this OH here. We actually have a chiral phosphoric, and it's an acid. So this is a way to provide a fairly potent, fairly strong acid that's chiral. And we'll talk about why you might want to do that later on in the semester. So this is pretty prominent for row 3 elements. So what about the corresponding row 2 elements? In particular, I'm quite interested in nitrogen. So nitrogen's in the same row in the periodic table, same group, same column of the periodic table as phosphorus. So everything I've just drawn, I could conceivably consider a version of for nitrogen. Well, sort of, not really nitrogen 5, right? Because that would expand the octet in a row 2 element. So in the phosphorus 5 example I have drawn, I've got phosphorus with 10 electrons seemingly depicted around it. We don't want to do that in row 2, okay? We can do that when we have d orbitals, but not in row 2 where the d orbitals are too high in energy. But what I want to consider is nitrogen atoms and chirality. I want to consider nitrogen atoms and chirality in situations similar to what we saw with phosphorus 3. That is, with that lone pair of electrons. So what I'm saying is, let's get a molecule like this, where we've got an ethyl, a CH3, and a phenyl, and then I'm going to put my lone pairs. I'm going to ask myself, am I chiral? Okay. This is kind of a crazy question because it's pretty easy to get to a normal nitrogen atom with 3 different things attached to it. I mean, honestly, if this molecule I have drawn here is chiral, and I should put a question mark, I'm asking a question. Ooh, clarify that, because the answer is going to be no. But if the answer to this question is yes, and this molecule is chiral, that really blows the door open on all of the nitrogen atoms that we use in life as we know it. That really kind of probably screws things up in terms of the timeline for evolution, slowing us way down, because now we have to figure out how to control yet another stereogenic atom as we build up our complicated biomolecules. For example, a nitrogen on an amino acid would only have 3 different things attached to it, because it has 2 hydrogen atoms, if we consider the non-protonated state. But now once we form the peptide in an amide, form the amide bond in a peptide and make the polypeptide, all of a sudden that nitrogen is chiral. Before that, we, for the most part, only had 1 stereocenter we had to deal with in our amino acid chemistry. So now we'd have 2, and then the universe has to figure out how to generate only single diastereomers in sort of the polypeptide formation. It could do it, it would probably just take a longer time to evolve for. So why is this not chiral? Because again, that would cause a lot of problems if nitrogen could be chiral using its lone pair of electrons. Well, it turns out that just fundamentally, row 2 elements rapidly, and so my row 2 elements would be carbon, nitrogen, oxygen, fluorine, for example, readily undergo lone pair, what's called lone pair inversion. Okay, lone pair inversion. That means to say that if I draw this molecule, let's just draw this molecule where we've got a phenyl, an ethyl, and a methyl. So this is the same as what I had drawn above. And I'm saying, hey, you know what? This is a chiral molecule because it's not superimposable on its mirror image. I'm just going to get rid of this because it'll just complicate things. Well, what happens is while this molecule is chiral on its own, it's rapidly undergoing lone pair inversion. So we don't have an opportunity for a permanent source of chirality or self-racemizing. Now what's happening is that the nitrogen sort of swallows it up and spits out the lone pair. It takes it in and pushes it out, takes it in the top and pushes it out the bottom. Maybe there's another metaphor like what spitting, but anyway, not appropriate, right? So it kind of takes in that lone pair and then ejects it out the bottom, and we've got the opposite, what I would call enantiomer. This is actually a better word would be invertimer. Or maybe I don't know. Invertimer, nobody really says that word anymore. But because we can access both chiral forms rapidly and in the absence of any catalyst, like we don't care what the solvent environment is, we can do this in the gas phase. This is just inherent to the molecule. Because of that, we're not going to see chirality form. Now, what's interesting is if you have a really complicated geometry, you can lock into one of these invertimer forms being higher in energy. And so all of a sudden, like if you have other stereocenters present, you can start to lock into one that makes a little bit more sense energetically. And similarly, protonation states could favor one form over the other if you have other stereocenters in the molecule. So there's an opportunity to take advantage of this downstream of this initial effect, but overall, for the most part, it's not seen. Okay. What we'll do in the, we'll break for now, but what we'll do in the next lecture is look at how chirality can emerge in NMR properties.